do a lot and they can get pretty lengthy. But you can think of this as kind of traveling down like a mountain path. You know, you had to walk down one path, but then you get off that trail and you had to get on another one. So you can kind of just, you know, add the two trails together. It's a longer resistance, even though they're two separate paths. It's kind of a similar concept here. So let's look at the resistor combinations. So if we were to say that we have resistors in series. So what does series mean? Series is going to mean that all these resistors are going to be on the same wire. Okay, so same wire series. And how do we do this? Sorry, it's acting a little funny. Okay, how do we do series combination? Well, what we're going to say is that R series is going to be equal to R1 plus R2 plus R3. Okay, and what that'll do for us is we can effectively take all three of those resistors and combine them together to create a new resistor, and it simplifies our circuit. Okay. So the series ones are the easy ones. The parallel ones is where it gets a little complicated. So let's take a look at a parallel situation. So here, parallel is if we have parallel lines, wires, separate wires, all with a resistance on it. So we'll call this R1, R2, and R3. Okay. So we see here that these three are all on different wires, and they all are connected. Okay. So the equation's a little strange, but we can write R parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3. But we can actually simplify this down a good bit if we do some basic arithmetic and multiply out. We can actually get 1 over R parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay. So these are going to be our, let's see if we can get that a little bit straighter. Okay. Our main equations for when we're combining resistors in this class. Now there is a special case. So this is a case where we have only two resistors in parallel with each other. So this will be R1, this will be R2. So here we can say our R parallel is R1 times R2 over R1 plus R2. Okay. But I can't emphasize this enough. This is if only you have two in parallel with each other. A lot of people in the past tried to use this when they have a situation like here. It won't work. So Like if we were to go and drop this in there, this no longer applies. Okay. And we're going to get a couple practice problems with these today. And we'll see it's actually kind of fast going through those. Okay. Current division. So now we know that current travels through circuits, but how does it travel through circuits? If we were to draw a quick diagram here, and where we had our two branches, so this is R2, this is R1, and this here will be a current source. So we know that current is going to leave through this battery, or this current source, apologies, travel through this way, it'll hit this point, and it'll branch off and send some through R1, it'll travel through, and it'll send some down through R2. But we want to know how much travels down each one. So the way we figure that out is we'll have to name this I1, and we'll go ahead and name this I2. So we can say that from our equation, I1 is going to be equal to R2 over R1 plus R2 multiplied by the source current. Okay. Now this is the equation the textbook gives you. Now there is a further simplification that I like to use and some of the professors like to use. From our combination of equivalent resistors that we had up here, notice that these two are in parallel with each other. So if you did R parallel, which is R1 times R2 over R1 plus R2, and we were to sub it into there, we would now get sub in. We would now get I1 is equal to let's see here. Apologies. Let's do this step first because this is the first step. Let's rearrange this for R2. So if we rearrange for R2, this will be R parallel times R1 plus R2 over R1. Then let's sub it in. And when we sub in, we'll notice that I1 is now equal to R parallel R1 plus R2 over R1. Okay, divided by R1 plus R2 times I of S. This mess, we'll cancel this out. This will give us I1 is equal to R parallel over R1 times I of S. This is just combining two concepts together to get another equation. It's up to you really which one you use. For me in this course, I'll be using this one here, but if you're working your problems, feel free to use either one. Does everyone see how I got to this part? All right. Okay. Well, then we'll move on to the next part. Voltage division. So voltage division will be where we take a voltage source and we have resistors that are in series. V1 plus minus V2 plus minus V3. Okay. All right. Um, R1, R2, and R3. All right. And what we're going to do is whereas up here, these had to be in parallel for current division to work. Here, these need to be in series for it to work. So what this will do is, if we know the current's going to leave this battery and travel throughout the circuit, it's going to pass through all these resistors, but we don't know what the voltage is across any of them. So to find that, we have our equation. Let's say we want to find the voltage of, we'll say R1. So V1 will be equal to R1 over R1 plus R2 plus R3 times the source voltage. Okay. And from what we saw up here in the combination for series circuits, we see that R1 plus R2 plus R3 is going to give us our series. So what we can say is voltage 1 is equal to R1 over R series times the voltage source. All right. And kind of an analogy that's been used in the past is you can think of resistors kind of like sponges. They soak up voltage. So you can think of this kind of as a pump. So whereas this battery is going to pump in water through here, it'll pump in water. Some of it will get picked up here, some of it will get picked up there, and some of it will get picked up there. So if all the water gets picked up by all three of those resistors, sponges, this portion here is basically just a percentage of the voltage source that's being pumped in. So it's a percentage of the water that's being soaked up inside the circuit pipe system. And we'll see, like I said, we'll see a couple of these problems in just a bit. And one last topic before we move on to problems, power. So power is going to be equal to VI. Now, there's two types, plus or minus, and it depends on the current. Okay, what does that mean for us? Well, if we were to say here, we have a battery and we have a current flowing through it, whatever terminal that current hits first is what we're going to assign to that current. So P is equal to V times negative I in this case. So this will give us negative VI. If we were to say the same current comes through a resistor, so now plus minus, P is equal to V times positive I. That'll give us positive VI. So if we have negative, that will be supplying power. And then if we have positive, that will be absorbing power. And you can kind of think that more in just the logistical sense. A battery will supply power and a resistor will soak it up. But do we have any questions on the concepts before we move on to problems? You can unmute yourself, or you can drop something in the chat.
I have a question.
Yeah, what's up?
So in the voltage division where it's in series, if we were doing resistor 2 instead of resistor 1, if we're looking at that one, would the voltage source be the same, or would it be like the voltage after it went through resistor 1?
Oh, no, and that's a very good question. So it would be the same voltage as the voltage source, because all that voltage is a percentage of the original voltage that was in the circuit.
Okay, because I was thinking that it might, like, you said it's like a sponge, so it's absorbing it as it went. So I figured it'd be a lower source going in.
Right, you know, and you're right on that thought. So if I was to go and say here, so just say, for example, there were 10 volts right here. So as you pass through here, you are going to lose a little bit of voltage. You might end up with you will end up with a smaller voltage over here. And then you'll travel through this one and you'll end with a smaller voltage on this side. That concept, you're absolutely right. But let's look at it kind of like if we were to write V2 out, V2 would just be R2 over RS times V of S. And then if we did V3, it would just be R3 over RS times V of S. And kind of with the percentage analogy, you can imagine it's kind of like, say 25% is soaked up here. 25% is soaked up here. How much is left to be soaked up? 50% over here. So it's kind of like that in a sense. So this V of S doesn't change.
All right, thank you.
Okay. All right. I'm going to take a quick 2-minute break. We'll come back at 6:36. All right, so let's go ahead and move on to a couple examples. Okay, on the sheet that I gave you, inside the PDF that I sent, this is just a quick example of how we can combine resistors in a circuit. So let's take a look at the first image here. They ask us to find the voltage across the current source using the circuits here.